Hello, so today, possibly a shorter video, I'm not entirely sure yet, but hopefully we are going to be deriving the electromagnetic wave equation, which should be fairly simple, following which we will prove for orthogonality between the electric field and the magnetic field and the propagation vector, which will hopefully be enjoyable. So first, first of all, I've written out the Maxwell's equations in a vacuum, hence a source-free region, lack of various things, for example, divergence of the electric field here is 0, and we've dropped the J term, so J equals 0, the current density, in the final equation. And so, to begin, we know it's, at this point we know it's a wave, so I'm going to assume a plane wave solution. So we can say E, or in fact I won't write arrows for this, of RT is equal to E0 little e to the I times K dot R minus omega t. And here K dot R is just, because R is just our directional vector. K dot R is, I could write it out, K dot R is equal to Kx x plus Ky y plus Kz z. Yeah, essentially. So this is our plane wave solution. And the first thing we're going to do is substitute this into, or rather apply the time derivative of the electric field for E. So we say that the derivative of E, I'm going to drop the arrows, is the derivative of this function, E0. To be clear, this is the maximum of the electric field. So the ik dot r minus omega t. We can pull it out because it's a constant. E naught, and then the derivative of e to the I k dot r minus omega. That's not very good. Omega t. That'll do. Now, we'll just do a substitution. Let u equal to I k dot r minus omega t, just to keep everything, in a comfortable manner. And then partial u partial t is minus I omega. There must be a better way of drawing this omega. I'm not very good at the lowercase one. I'm not very good at the uppercase one either, to be honest. So now we can say that the partial derivative of the electric field is e to naught e to the u times this minus I omega, which is e to the u times e naught. That's just our definition of the electric field. Sorry, of the of the electric field. So, or rather of the electric plane wave solution. So this is just minus I omega e from our definition up there. So we can say that for this instance, the partial operator with respect to time transforms as minus I omega. The second step would then be to deal with nabla or del or whatever. So I'm sure you understand what it's defined as, but I can write it out just to be sure. I have it in my notes, so I may as well. Is x hat times the partial derivative of x plus y hat. This is the norm vector in direction x, y, and then z will come in a moment, plus z hat partial z. Now we can substitute in this is why our definition of k dot r is kind of useful, because now we can sub that in and I'd have it written down. Partial e, partial x even in this circumstance, and then this would be repeated for the other operators, which I'm not willing to write out, but we can at least see how the differential operators transform on the electric field. So this would be E naught times the partial derivative with respect to x of e to the I, kx times x plus ky times y plus kz times z, minus omega t, don't forget. What does that equal? Well, it's E naught times differentiating this, I k sub x, because we're with respect to x, e to the, and then back to our original function, which would actually just be e, so I can write that in. No, I should write in the full thing, because I've got the, okay. E to the I k dot r minus omega t, which is just I k sub x e, hence, or rather further, partial with y, so partial with partial x corresponds to I times kx, partial with respect to y corresponds to I ky, and finally partial with respect to z corresponds to, why does it keep jumping? Corresponds to I kz. Exactly as it might. You can do that, but I think it's fairly obvious how that would be shown, because if you differentiate here with respect to y, then these would just be constants and y would come down, and same with z. And then you'd left with that same function up there, because exponentiation, am I right? So now we can see what divergence is for the electric fields. So, well, the full definition of the divergence of some field F is the partial of the all the different axes. That's the word I'm looking for. So we have one with respect to x, because this is in R3, so we have x, y, and z. Obviously, those are just arbitrary names. It could be A, B, or C if you wanted. Ez with respect to z. So this is our definition of the divergence of E. But obviously we know what these operators are doing, because we've defined up here what they're doing. So we can actually just write this as I k sub x of E sub x plus I k sub y. That's not a very good k, but we'll deal with it. E sub y plus I k sub z of E sub z. Take out the I from all of this, and we get k sub x, E sub x plus k sub y, E sub y plus k sub z, E sub z. What is this? Well, we have our vector E and its components, and also Z and its components. So this is just the dot product of two vectors k and E. And what is k? K is our directional vector, so, or rather propagational vector. So it portrays the direction of wave propagation. In fact, further to this now, we can say that for this circumstance, the divergence operator, KF, some field transforms as I, K dot F. Because that would be expanded and it would just be IK, because this is multiplicity, that sounds right. Finally, the last operator, which we can see how transform, the last operator that we can analyze the transform of is curl. And what is curl? It's well, you'd have to take it for each operator in this circumstance, so I'm just going to solve for the curl in the x, and then the other ones could be done in a very similar manner, as I'm sure will be apparent. Is the partial of Ez with respect to y minus the partial of Ey with respect to z, which is Ik from our definitions above, Ik sub y E sub z minus Ik sub z E of y, E of y, which is I bracket K cross E. So for our x curl, we end up with this. And so you do the same thing for x, and this would be y. Do the same thing for y and z, and these values would change. That would be z. For y, that would be z. That would be x. That would be x, and that would be z. And then same for z, except that would be y. I think, yeah, that sounds right. Yeah, because then, yeah, okay. So therefore we can say that the curl operator on some field f transforms that field in this circumstance as Ik cross f. So now we have what all of our properties transform as, which is great. This will be more useful for later when we are, because when we're proving orthogonality, basically none of this, the wave equation derivation is far easier than this because we can just use vector identities. Everything we've done so far to find out this and these and the other ones are here and here. Did I miss the gradient operator? No, I didn't. Okay, so the benefit of this will be for our proof of orthogonality. Deriving the wave equation is not so hard. What we will first do is take Faraday's law. So the curl of the electric field is minus the change in the magnetic field with respect to time. And then we will take the curl of that on both sides. And space and time derivatives commute, so you can then take the derivative out here. So it would be minus the change in the curl of the magnetic field with respect to time. Why did I write that? Why did I write the arrow in? Who knows? Bye arrow. And that's still the curl of the electric field. Now we can take the other the definition from the fourth rule, Ampere's law, maybe. Yeah, I think it's Ampere's law. What we know that is, so we can say that this is minus the derivative of mu naught. No, must not draw them like that. That's how you draw an epsilon. Epsilon naught partial E with respect to t, and because they're both with respect to t, that's just minus mu naught epsilon naught partial squared e with respect to t. So, yeah, that's good. Now we have the vector identity, which is the curl of some field f is equal to the gradient of the dot product of the field minus the Laplacian of the fields, and Laplacian being that squared, which is the local something of the something, remembering the wordy definition of it, the local curvature of the field. Yeah, sure, that sounds okay. That's what I've got written on my notes. So now we apply this to the left-hand side because we have that identity, and so we can say that, because we just swapped e in there, so the gradient of this, the dot of e, minus the Laplacian squared of e is equal to minus mu naught epsilon naught partial squared e partial t squared. And now we have everything in terms of e, which is nice. But we have Gauss's law right at the beginning somewhere. Yeah, there we go. The dot, or rather the divergence of the electric field is 0, so get rid of those because that goes to 0. Laplacian of e is mu naught epsilon naught times the second derivative of the electric field. Okay, so the last thing that I want to do as well is just, we know that c is equal to 1 over the root of mu naught epsilon naught. Hence, if we swap over root mu naught epsilon naught is equal to 1 over c, mu naught epsilon naught is equal to 1 over c squared, and hence e is equal to 1 over c squared times the, I won't put that in, I'll just write partial e t squared, and also b is equal to 1 over c squared, so it is literally identical for the magnetic field. So this is our wave equation. Now this can be solved for a plane wave solution that would be in that form, e naught e to the I bracket k dot r minus omega t. But I already know that, and the main idea of this was more to show the orthogonality between all these, because you see those cool diagrams where it's like, it's gonna be the worst drawing ever, but it's like that, and then electric field or whatever, and then magnetic field, and it's like, well, how do they know that it's like that? And I thought it would be cool to show that. I'm already getting my diagram wrong. That goes down, that goes up, and that goes sideways, and then that goes down, and then that goes across. Yeah, whatever. And this would be K in this case. We could say that's E and that's B. Regardless, I'll leave that beautiful diagram there. Regardless, let's continue so I can show that. First we'll show transversality. So from Gauss's law we know that equals 0, Gauss's law, yeah. Now we know what this does from our definitions above. I'm not going to keep scrolling up and finding them. I'm just going to write it in. So ik dot e equals 0, hence k dot e equals 0. We can get rid of that because we're only looking for the real components here. Since the dot product is 0, we know that it's equal to 0. Or rather, dividing both sides by I. Nothing to do with it. Ignore me. Since the dot product is 0, these two must be orthogonal. Hence, the electric field, I can write, therefore, the electric field, I'll just write that they're parallel, perpendicular. Obviously, perpendicular is weak in 3 dimensions, which is why we say orthogonal, but that's okay. Similarly, you can do the same thing. I'll do it quickly. B equals 0 implies that ik dot b equals 0, k dot b equals 0, therefore b, so therefore k must be in a direction that's orthogonal to both e and both b, thus it propagates perpendicular to this is the GCSE physics definition. The direction of energy transfer is perpendicular to the propagation, or perpendicular to the direction of movement, or whatever. It's like water. That's the definition that I had to learn last year. This is a bit more robust, I'd be willing to say. Now the last thing we want to prove, because at the moment E and B could be in the same plane, so the last thing we could prove is orthogonality between E and B. So we can take Faraday's law. I think this would work as well with Ampere's law, but I'm going to take Faraday's because that's what's in my notes. Yeah, we should be familiar with that by now. Again, we have derived operators for both of these, so ik cross E equals minus times minus I omega b. Those would cancel, there's an I on both sides, like that. So k cross E is b, is omega b. And thus b is equal to 1 over omega k cross E. What does this mean? Well, by definition of the cross product, b must be perpendicular to both vectors in the product, because that's what the cross product is. Thus, b is, well, this proves again that b is proportional to k, perpendicular to k, but therefore I can write, by definition of cross product, b is perpendicular to k, E is perpendicular to k, and B is perpendicular to E. Hence, they hold orthogonally, and we can pop that in a box. I don't think this was particularly long. Well, no, it was about half an hour, but it's pretty cool that we can, show this. Although some people did it 100 years ago. Anyway, I hope you enjoyed, and I'll see you next week for another video.